In this video we're going to be applying calculus to polar curves, and I'm not going to be reviewing the basics of polar coordinates or polar graphs, so review those before you watch this video. So our first problem is coming up with an equation for the slope of the tangent line to a polar curve. So the easiest way to do that is express the polar curve with a set of parametric equations, because we already know the formula for the derivative of a parametric curve. It's just dy dt over dx dt. So to express the polar curve in parametric form, if we have a curve equals a function of theta, then we can use these equations: x equals cosine theta and y equals sine theta, and just replace the with the function of theta. And then x and y will both be defined as a function of theta, which is a parameter. And so then it's easy to find the derivative. Since a parameter is theta instead of t, the equation for the derivative becomes dy d theta divided by dx d theta. And then to find these, we just differentiate these two expressions with respect to theta using the product rule. And then once we get this, we can simplify them by replacing f of theta with and f prime theta with d theta. So a final expression for the derivative of a polar curve is cosine theta plus d theta sine theta all over negative sine theta plus d theta cosine theta. So let's say we want to find the derivative of the circle equals 4 cosine theta when theta is pi fourth. So to use this formula, first we just have to find and d theta. So is 4 cosine theta, and then d theta will be, we just differentiate this to get negative 4 sine theta. And so once we have these, all we have to do is plug them into this formula. And then we can simplify this using double angle formulas to get negative cosine 2 theta over sine 2 theta, which is just negative cotangent of 2 theta. And then if we plug in pi fourths for theta, we get negative cotangent of pi halves, which is 0. Now since the derivative is 0, we know that the tangent line will be horizontal when theta is pi fourths. Now if we want to find the tangent line that crosses through the origin, we can use a little shortcut. So at the origin, is equal to 0. So in our formula, these first terms will cancel out because is 0. And then after that, these d thetas will also cancel out. And so what we're left with is tangent of theta. And we can call theta naught the angle that it makes when is equal to 0. So we know when is equal to 0, the derivative of is just tangent of theta. But tangent of theta naught, is also the slope of this line, theta naught. Because opposite over adjacent is the same thing as rise over ren. So we know that this line, theta naught, has to be equal to the tangent line at the origin. So in other words, whatever the theta is when is equal to 0, that's going to be one of the tangent lines that crosses through the origin. So say we want to find the tangent lines at the origin of the rows equals sine of 3 theta. So all we have to do is find what theta equals when is equal to 0. So sine is 0 at 0, pi, and 2 pi. So we set those equal to 3 theta, and then just solve for theta. So our tangent lines that cross through the origin will be 0, pi thirds, and 2 pi thirds. So next we want to find an arc length formula for polar curves. And we just apply the same formula that we used for parametric curves, using the expressions for dx d theta and dy d theta that we found earlier. And so if you do that and simplify it, you'll get this expression. So our bounds of integration are alpha and beta, which are angles. And then so we have the integral of the square root of r squared plus dr d theta squared. So if we want to find the arc length of this spiral, r equals e to the theta, between theta equals 0 and theta equals pi. So 0 and pi will be our boundaries. And in this case, r and dr d theta are the same thing, since the derivative of e to the theta is just e to the theta. So we just plug those in, simplify, and then we can integrate to get an answer. So the last thing we want to find is an expression for the area enclosed by a polar curve. So remember when we were in rectangular coordinates, to find the area under the curve, we divided it into small regions, which we approximated as rectangles. So for polar curves, we're going to divide the area into very small wedges, and then we can approximate these wedges as a sector. And we can easily find the area of each sector, because the area of a sector is just 1/2 r squared theta. So the area of each of these very small sectors will be 1/2 r squared d theta, where d theta is just a very small theta. So then if we want to find the area of the whole area from alpha to beta, then we just integrate to add up all the areas of these small sectors. So we get the integral from alpha to beta of 1/2 r squared d theta. So let's say we want to find the area enclosed by this cardioid, r equals 1 minus cosine theta. So the first step is we have to determine our bounds of integration. One way to do this is imagine a line that goes from the origin to the curve. And then imagine what angles it has to pass through to sweep out the whole area of this curve. So here, it has to start at 0 and then go all the way around to sweep out the whole area. So our bounds of integration will be 0 to 2 pi. And then once we determine the bounds, all we have to do is plug in r and then integrate. So here to integrate, we had to use the double angle identity for double cosine to simplify this cosine squared theta. So once we do that, we can just integrate and get our answer.